Hello, good afternoon everyone. Welcome back to my channel. My name is Marina. I have master's degree in nautical science and this is Celestial Navigation making of textbook part 3. This is third video of the series, and as you can see I'm working on my next textbook and I'm recording the process, and I'm also explaining you what I'm doing during the process. So in the first video I covered the procedure how to get the data for known star, known planet, and then in the second video I covered sun at any moment, sun at noon, so in moment of crossing our meridian, and sun at sunrise and sunset. The procedure how to calculate deviation of magnetic compass by observing sun at the moment of sunrise or sunset. Schedule for today is Polaris, so North Star, and unknown celestial objects. So how do we identify an object if we have measured his bearing and height of an object that we did not identify? We don't know which one it is. So usually in practical celestial navigation you avoid that. You don't actually take sighting of an unknown celestial object. You just pick one that you know, so it's faster and easier for you to get the solution. Okay, the calculator is on my left, on the left side of the screen. You can see everything. So let's start with Polaris. So let me change the data for the task. So we have observer is observing Polaris star, and let's change this to uppercase. So Polaris star, and the date of observation is 04 of July. The year is not important because for the year I'm using my own nautical almanac. If you want to buy it, it's nautical almanac for education. It's specifically designed for education. It can be used for practice. It is in every way, shape or form similar or identical to nautical almanac that you can buy annually for your ship, but it is designed for education, so it has some extra features inside that can help you when you are calculating celestial navigation. So link for that is in description. The position assumed of observation of Polaris is 21 degree, 30 minutes exactly, 30 minutes north, and longitude of observation is 140, 48 minutes. 48 minutes, and it's not west, it's east. Another data that we have given when we have observation of Polaris is ship's chronometer error, and in this case our ship has only 10 seconds but positive. Usually the positive sign is not marked, but just to avoid confusion I emphasize that the ship's chronometer error is either negative or positive by placing either minus or plus in front of it. So I don't skip the plus, I put the plus, so candidates know 100% they are sure that it's not negative. Height of the eye is larger, is 21 meters. Sextant error is, we have a big sextant error, 2.3 minutes. So that's index error, that is permanent error provided to us by the manufacturer. We cannot correct this, so everything that we measure with this sextant device will have error of minus 2.3. Temperature is 10 and pressure is 1013. And also we have time of observation, chronometer time is 20:11:45. So that is the time of observation that we read from our chronometer on our ship. And height observed with sextant is 22 degrees, 14.4. So 14.4. Also we have another set of informations, and that is that compass reading or azimuth is 357.5 degrees, and variation from chart is 1191 is 1 degree 18 minutes west, and annual change is 4 minutes east. Okay, so it's asking, so this is the task, and it's asking from us to calculate latitude of observation. That's the benefit of Polaris. Polaris gives us directly the latitude of our position, not like any other star that gives us angle and error. So it doesn't give us one of the coordinates directly. Polaris star gives us directly latitude of observation. And we also have to calculate the error of our compass. We have to calculate deviation of our compass by using the compass reading and variation from chart. So first step is always the same. We cannot do anything without knowing the exact time. So our time is 20:11:45, and the error is just 10 seconds, and 10 seconds positive. So that means we are at 20:11:55. So this is the exact UT time of observation, and the date remained the same, so it's 4th of July. We didn't cross the midnight, so the date stays the same. So this is the date that we need to use to enter the almanac, and we need to find the correct date page. So we are looking for 4th of July. 4th of July. Let me get 4th of July. Where is it? So it should be somewhere in the middle. July is middle. June, July. Okay. And because Polaris is star, we are not reading the data for star directly. We are reading the data for Aries, so spring point. That's our closest star, sun frozen in point of spring. So I need Aries on 4th of July. Let me take a screenshot of that so you can see it. So, okay. Let me copy that here. Okay. Now this is too big. I'm going to close it here. So I'm looking 20. So that's, let's copy this, copy, and make it bigger, slightly bigger. So first we need this, we need red, and then we need to read the correction for minutes and seconds. So first we enter the almanac on 4th of July with 20 minutes, and for 20 minutes, local hour angle is, calculate local hour angle of Aries. We only need Aries. So Greenwich hour angle of Aries at 20, and 11:15 will be the error that, or 55 is that we need. So here we have page. Let me show you the entire page so you can see where I'm taking this data from. Ooh, let's see. Where is PDF? Here. Okay. So this is the page I have. So on the top I found July 234, and I'm on page where I have Aries, Greenwich hour angle. So the first date is 2nd, and then the second date on the page is 3rd, and then the last date on the page is 4th of July. That's what I need. And I need 20 or 8 p.m. so 20 hours, and that is 223:11.9. So 223 degrees 11.9. That is Greenwich hour angle of spring point Aries. And that's it. That's the only information I need from this page, and I can automatically go here to increments and corrections, and I'm looking for 11 minute 11. So let's go 8 10. So here I should have 11 minute and 55th second. So that's all the way on the bottom of the page. Now you will have this book in front of you, so you will see the top of the page, but I already know that. So the first column is error for sun and planets, the second column is error for Aries, and the last column is error for moon. So I'm looking at the second column because I'm looking for Aries, spring point, and for 55, the correction is 2 degrees 59.2. So 2 degrees 59.2. That is correction for minutes and seconds. So let's go back to the textbook. So with this number and the date, I got this number here. I got Greenwich hour angle for exact hour, and then I enter increments and correction tables with 11 minute and 55th second. And under Aries, I read the correction to be 2 degrees 59 minutes. Now, after I have that, I need to add my longitude, and my longitude was 140.48. So 140 degrees 48, it's positive east. Now, when it comes to Polaris, we do not need her distance from Aries, and we are looking for Greenwich hour angle of Aries. Come on, Greenwich hour angle of Aries. So let me move this. Local hour angle of Aries. So this is unique when you have Polaris. When you have Polaris, you do not actually need her distance from you. You just need to know how spring point is away from you. You need to know local hour angle of Aries. So we have 223 degrees, 11.9 minutes, plus 2 degree, 59.2, plus 140 degrees, 48 minutes. And we get the number, so I'm going to do it here as well. In a real situation on ship, you would not write this down because you automatically know this number cannot be, because it's over 360. LHA is measured in an arc of 0, 360, cannot be under 0, cannot be negative, or greater than 360. So in our case, we need to subtract from 360 because we got the result that is over 360. So the correct is 6 degrees 59.1. That is local hour angle of spring point Aries for our moment of observation. So on this date, this hour, this minute, this second. Now that we have local hour angle of Aries, we need to round this number up. So this number rounded is 7 degrees. So because this is 6.99, I can also show you that on the calculator. So you just press the DMS button. So it's 6.985, that's 6.99, or that's 7 when you round that up. So it's 7 degrees. So let me put the sign here. So it's not 7 degrees exactly, but what we actually do is, let me see, do I have that mark? Do I have that mark? That will be under math. I'm looking for equal sign that is curved. So curved equal sign is actually a sign for approximation. So we approximate that to a round number. Where is the, so let's look for the curve equal. It's under math. I know you cannot see what I'm searching, but I have a full list of math symbols, and I'm just looking for the symbol I need. It's supposed to be here under math symbols. So yeah, this one, here. So this is what I was looking for. So we approximate that to the full round number. So local hour angle of RES is actually 7 degrees. That's rounded, so rounded. And now after that, we need to correct the height observed to get the height true. Now all of these corrections that we have here are due to the fact that we have a dip, because we are not looking at the star from true horizon, sea horizon, but from a certain height above the water level. And also you have refraction and parallax. You have different distortion caused by Earth's atmosphere and density of the Earth's atmosphere and density of space. And all of those corrections are accumulated in a couple of tables that are usually in front or on the back of each almanac, and they're always same. So no matter what almanac you are using, you can use the same height or altitude correction tables. So the height observed was 14.4. Index error was 2.3. So that is the information we got from the box of sextant, box of our device. And now we have to read these 3 corrections. So this was from the old task. Let's delete that. So we need to get the dip. Now our height of observation was 21 meters and our height observed is 22. So let's get height correction tables. Height correction tables. Let me show you the PDF file. Okay, so we have height of star. So height of star of planets, that's the name of the table. On the left side, we have sextant height, so we are looking for 22. And on the top, we need 21, because the task is height of R is 21. So from the top, we enter with 21. From the left, we enter with 22. And the correction is, where those two numbers intersect, is minus 10.6. So the correction is minus 10.6. Minus, so that's the dip, minus 0 degrees, 10.6 minutes. And now we have correction for temperature and pressure. So once again, we need to find the table for temperature and pressure. And if we go there, let's go there. This table is also on the back of Nautical Almanac. So we enter this table with 22, so that's here, that's the second column from the left, 22, and the temperature is 10, so the correction is 0, and the pressure is 1013, so those two values, 10 degrees Celsius and 1013 hectopascals are standards for this table. So every time you have 10 degrees Celsius and 1013 hectopascals given as temperature and pressure, you automatically know that the correction is 0, because the correction here is calibrated for that pressure and that air temperature. So both corrections are 0, so we can skip that. And that is one of the reasons people usually in real life, they do not actually read the correction. This is something that is only done in school when you are practicing, because in 900 out of 902 times, the correction for temperature and pressure turns out to be 0, or they are canceling one another. So we have 2214.4, and we have minus 2.3 and minus 10.6, and once we calculate that, we get what is that? That is 12.9. So that means that is 22 degrees, 01.5 minute. Now you can do this with calculator. Just keep in mind that this value has 0 in front. So 0 degrees, 2.3 minutes, 0 degrees, 10.6 minutes. And now there is something very unique that is happening in the step number 5. Let me just copy number 5. Oh, I'm going to need this later, so I'm going to copy all of this. So step number 5. Copy. So special altitude corrections. Sorry. For Polaris. So Polaris is a very unique star because it is approximately directly above the North Pole, and North Pole and South Pole is actually connection of the Earth's axis of rotation. So basically Polaris is one of the rare stars that is apparently not moving, unlike any other stars around her. So because of that, Polaris has its own unique tables, and if we add those corrections from that unique table, we're going to get our latitude. So let me copy this. Why is it? Let's see, how can we fix this? Like this and like this. Okay. So we start the process with height true. Usually you will not split this in step 4 and 5. Usually what you would do is you would just continue with this one. After this one you have height true, and you would just continue with correction 1. So correction 1, and then you have correction 2, and then you have correction 3. And this one is extra. Let's delete it. Copy. Layout. Delete row. There it is. So this is lat of Polaris. So step 4 and 5 are usually done together, but just for the sake of this video and for the lecture, I'm going to split them. But basically, after you get height true, what you do is you add these unique specific corrections that are only valid for Polaris star. And basically what these 3 corrections are is when you summarize this correction, this correction, this correction, so these 3 corrections together are actually distance of Polaris from the North Pole. That is what these 3 corrections represent. So if Polaris was exactly directly above the North Pole, the height of Polaris you measure would actually be your latitude. But because Polaris is a little bit shifted from the North Pole, we need to add on the height measured, we need to add specific 3 corrections to get our latitude of observation of Polaris. So let me show you the specific tables that Polaris has. Now these tables can be different from almanac to almanac. These ones are the most common one. So basically what you have is you have Polaris pole star tables for determining latitude from sextant altitude and azimuth. Okay. So you enter this table with local hour angles. Here you see it says local hour angle. And then you have 0, 10, 20, 30, 40. So you have every tenth of local hour angle on the top. And the last digit of local hour angle is actually here. And that is how you get the first correction. So for example, if local hour angle was 123, you would look here for the full number that is 120. 120 is here, this column, and then the last digit is 0, 1, 2, 3. So under 3, 123, and the correction is minus 5.3. If the local hour angle was 138, you would enter under 130, and then the last digit is 8, and under number 8 you have correction. Once you find the column of local hour angle, you stay in that column. So for 138 you would find 130, and you will stay all the time in the 130 section. And the first correction would be with the last digit of local hour angle. Second correction would be with approximate latitude, just approximate latitude. And the last correction will be with the calendar month of observation. So in our case, our local hour angle is 7, so it's actually 007, so the last digit is 7, and the first two digits are 0, so we enter column 0, and the last digit 7. That makes first correction minus 34.9, so minus 0 degrees, 34.9 minutes. That's the first correction. Second correction is for latitude, and our assumed or our latitude was 21, so that is close to 20, and we can see that for 20 and even 25 the correction is 0, so that means second correction is exactly 0, so 0 degrees, 0.0 minutes. The third correction is for calendar month, and the calendar month is July, so 4th of July, and third correction is minus 0.3 minutes, so negative 0 degrees, 0.3 minutes, 0.3 minutes negative. Now, while we are still here on the same page, there is also one more thing that we can read out. On the bottom of the page, we have a special table for azimuth, and here we also enter with local hour angle, so we stay in the same column, 0, and our latitude was 20, so that means the true azimuth of Polaris in degrees is, so azimuth true, let me get that, azimuth true is 0.5 degrees. Okay, so that is how you use these tables for Polaris. You enter with local hour angle. Local hour angle is a 3-digit number. The first number is the second number and the last number. First two numbers you look on the top, so if it's 10 you go here, if it's 15 you go here, because the first two digits is 0, 1. So if it's 120, the first two digits is 1, 2, so you enter in 120, 120, and the last digit of local hour angle is entered from the left side to get the correction. And once you find the column, you stay in that column. The second correction is obtained with latitude of the DR position, and the third correction with calendar month. And after you do that, you can also, while you are still here, write down the azimuth of Polaris. So this is a true azimuth of Polaris in degrees, and you enter the column with latitude from the left, and on the top you stay in the same column as before. Okay, so let's go back to Word file. So let me put layout, let me put another set of columns here, no border. Okay, so this is height true, that is actually corrected, and then we have first correction with last digit of local hour angle of Aries. This is with lat of DR position, and this is with calendar month. That is how we obtain these three corrections. And this is latitude of our position of observation. And now once we put all of this in calculator, so that would be 2 degrees, 14.4, minus 0 degrees, 34.9, minus 0 degree, 0.3 minutes, equals 2139.2. So 21 degree, 39.12 divided by 6 is 2, so that's 0.2 minutes. Okay, how did I get, yes, 22. Oh, height true 0.5. I'm looking, I get a strange number. So height true is 22.1.5. So I can easily fix that in calculator. If you have a new version of calculator, you can just go back. You don't have to type everything again. You can just do this and you get the result. So 26.3. So what happened here is I just copied the height sextant in the first row. I didn't copy the height true. So that's one of the reasons why I told you that usually step 4 and 5 are one step. You just continue this process here. You just continue doing it and you get to the latitude of Polaris with all of this in one session. And azimuth true, so azimuth true is obtained with LHA of Aries and lat dr position from special tables, special Polaris tables, so only for the Polaris star. And now we can go to step 6. Now step 6 is asking us to calculate correct variation for the year of observation. So the year of observation was 1991, I believe. Let me check. Yes, 199, and it was 1 degree 18 minutes west, and annual change was 4 minutes east, and we need variation for 2018. So we have 2008, so variation is negative because it's west, minus 1 degree 18 minutes multiplied with 4 minutes times number of years. So how much we have 8 plus y, we do this when we can do this, minus 1991 equals 17 years. 17 years. So we have this. So 17 years times 0 degrees 4 minutes is actually 1 degree and 8 minutes. So 1 degree and 0.8 minutes. And because the first one is west, so minus 1 degree 18, we're going to get some very small number. We're going to get negative 10. And if we round that up, that is 0.16666. So that means that is 0.2 negative or west. That is variation for 2008. So negative 0.2 degrees west. And now we have to calculate deviation of magnetic compass. Azimuth true that we measured was 0.5 from the table. From the compass it was how much? Let's go back to the task. Compass reading was 357.5. So 357.5, and variation is negative 0.2. So we have 0.5 degrees minus 357.5 degrees minus 0.2 degrees equals, and I'm going to write this down. I know this is not correct, but I'm going to write it down, 356.8. Now, deviation cannot be this large, obviously, it's not possible. So if we get deviation larger than 180 in either direction, so in either direction, either negative 180 or positive 180, we need to add 360 to that value to get the actual value, so it's 3.2. So deviation of our magnetic compass is 3.2 degrees. Okay. And that is how you calculate latitude by using Polaris observation, and deviation of magnetic compass using, once again, Polaris observation. and this is step 7. That's it. I can shrink this a little so everything fits on the same page. Yeah, okay. So that's it. So let's go back to the beginning. We can put this here under 20. So this is where I got the value 20. Observer is observing Polaris star at 4 of July at assumed position, latitude and longitude. Ship's chronometer error, height of eye observer, index error of sextant, air temperature, air pressure, time of observation, height observed, compass reading from magnetic compass, and variation from chart. First step is always to find the correct UT time and date, because without that we cannot enter nautical almanac. So once we find the correct UT time and date, we find the correct date page in almanac and we look under Aries, under Aries column, and we just read the local the Greenwich hour angle at that time. So 4th of July, 20 hours, 223:11.9. Then we go to special increment and correction tables to get the correction for 11 minute and 55th second under Aries column. And once we add our longitude to that number, we actually get how far the spring point of Aries is away from us, our position, our meridian. And that number we round up to a full degree. Usually if it's 6:20 minutes, you go 6. If it's 6:40 minutes, you go 7. If this is a master exam over 3,000 gross tons, then you cannot do the rounding up. You have to use the interpolation. So you have to interpolate the correction between the two values. But in our case, we have 6.98, so that's very close to 6.99, or that's extremely close to 7, so we can use 7 degrees. We do not have to make interpolation from the tables. So after that is finished, we need to correct the height observed to get the height true. We have sextant error that is permanent for that device. We have horizon dip because we are observing star from our horizon of our eye, not from the water level, and everything in the tables is adjusted to the horizon level of the sea. Temperature correction and pressure correction were 0. And after we added all those corrections, we got height true. On that height true that we measured, we add special 3 corrections unique for Polaris star. Actually, these 3 corrections, when you summarize them, the total value is actually how far the Polaris star is off from the celestial North Pole. If Polaris star was exactly above the North Pole, then the height true would be your actual latitude. So this is latitude of our position of observation. From the same page where we have Polaris special tables, on the bottom we have table to get azimuth true. Azimuth true of Polaris deviates from 2 degrees to 358 degrees throughout the year, so it rotates between those 4 numbers. So we have azimuth true from the tables to be 0.5. Then we have variation from the chart for 1991, and then the year of observation is 2008, and we converted variation from the chart to our year of observation. And after we have that, we have azimuth true, azimuth compass, and variation. Those 3, when you subtract them from one another, you get deviation. Deviation cannot be larger than 180 degrees. So if you get it larger than 180 degrees, it is actually opposite value. So in our case, we have it negative and larger. So we need to add 360, so plus 360. Plus 360 degrees, and the actual deviation of our compass is 3.2 degrees. So that means whenever I'm reading something from the compass, it has an error of 3.2 degrees plus variation on the chart that for that area where I'm currently my ship is located. And this is something that you need to check regularly. like once or twice a month, or depending on how, in what direction you are traveling, you need to check it more often or less often. And deviation in original state is given to you by the shipyard, and after you get the ship from the shipyard and you start using it, you need to do the control of deviation. So basically the title of this should be latitude, lat by Polaris, and control of deviation. We say control of deviation because we already have deviation, we just need to control it. If we have the table given to us by the shipyard and it says that deviation is 3.2 and we get 3.2, that is how we control the deviation. Is the number changed? Has the number changed, or is it still the same? And that's it for the Polaris star. Okay, and let's go back to the next task. Next task is unknown celestial object. So let me copy the data so it's easier to type. Copy. So observer is observing unknown celestial object. And the date of observation is, let's see. Oh, it's 4th of July for the example. So let's use the same date, but the position is different. It's 26.0 south and 164.36 west. 36 west. Chronometer error of ship's chronometer is 2 minutes and 43 seconds, and it's negative. Height of eye is 21. It's the same ship, so the same sextant, same error, negative 2.3. Temperature is the same, 10 degrees and 1013 hectopascals, so that's the same. And height of observation, let's first get the time of observation. Time observation is 05 2548 05 2548, and the height observed of this unknown object is 24.9. That's the height measured with, or altitude measured with the sextant. Compass reading is, let me see how much is the compass reading. Compass reading is 334 degrees. So 334 degrees. And variation is information that we're not going to use. Okay, so we have height observed with sextant to be 35 degrees, compass reading is 334, and we need to identify this object. So I'm going to, because the unknown object cannot be sun, cannot be moon, and because of that it can be either star or planet, and I'm going to use the procedure for either star or planet, doesn't matter. I'm going to take this, because once I calculate the data, it's going to be either sun or either star or either planet. And also the first step is always correct UT time. So the first step is to get correct UT time. Our time is 05 2548. Error is negative 243, 2 minutes and 43 seconds. So that means 5 hours, 25 minutes, 48 seconds minus 0 hours 2 minutes 43 seconds equals 5:23:05. So 5:23:05. So that is my exact UT time, and we did not cross, or did we cross the midnight? We have to check now. Did we cross the midnight? We are at we are at 164 degrees west. So that means we are in time zone 11. 164 divided with 15 is 11. So that's time zone minus 11. So our time of observation is, okay, so I'm going to make a note here, 0307 locally. So what that means, that's not how you spell locally, right? So that means when we are observing this unknown object, our date is 3rd of July, while in Greenwich is already 4th of July. The reason for this is time zone minus 11. So because it's west. So if I'm observing the unknown star on 4th of July, in Greenwich is actually 5th of July. So that means the dates are different. So if I have 3rd of July, Greenwich has 4th of July. So if the date, this is important, if the date in the task is given to you as a local date, then you need to correct it, especially if your longitude is west. You need to be careful, did you cross the midnight, or did Greenwich cross midnight, and it's actually in the next following date. But if the date is given to you as the date belonging to this chronometer time of observation, so this is Greenwich date and Greenwich time, then you do not have to correct it. So basically, this observer is observing unknown celestial object at 3rd of July locally, and Greenwich date is 4th of July. So it will be written in the task, it must be written in the exam when they have date, is it local or is it Greenwich date? So in our case, we are still on the 4th of July because this task that I'm using, for example, this is Greenwich date and the local date is 3rd of July. And now we need to calculate the local hour angle of Aries. That's the benefit of spring point. Everything that is on the sky can be referenced back to the local hour angle of Aries. So in our case, we do not know is it planet or star, so we're going to use Aries in our advantage. So it's going to be Aries here and here. Not like that. And go red. So Greenwich hour angle of Aries on 4th of July at 5:23:05. So that means we need to go to the almanac and get the Greenwich hour angle on this date. And because it's 4th, I can use the image I had above. So I'm looking Greenwich hour at 5 o'clock. So it's 357:34.9. So I can copy this because it's the same date. Copy. I'm going to use it here. So 5 in the morning means 357 degrees, 34.9 minutes. So that is Greenwich hour angle of Aries at 5 o'clock in the morning. And now I need to get correction for 23 minutes and 05 seconds. So that's increment and corrections table. Increment and corrections tables for 23:05. I'm just going to switch so you can see what I'm doing. So you open the table with increments and corrections and you look for minute of 23. So 23 is here. and 05 second and Aries. So that correction is 5 degrees 47.2. So 5 degrees 47.2. So that is my corrections for 23rd minute and 5th second Aries. Now I have that correction. The thing that remains is my longitude, and my longitude is this one here. And I need to make a note. It's negative because it's west. So let me just put this on the same page so everything is on the same page. Okay, so I have this. Let me delete this. Local hour angle of Aries. So I have 357 degrees 34.9 minutes plus 5 degrees 47.2. That's my increment and corrections, and negative because it's west 164 degrees and 36 minutes equals 198 degrees 46.1 minute, and that's it. We don't have to correct it. It is in the arc where it should be and where it can be, between 0 and 360. And now we have to correct the height observed to get the height true. Now we can do this by using the same tables, because the unknown object will be either star or planet, and the correction for star and planet is one table, so same table. So it doesn't matter at the end, once we find out is it a star or planet, the correction of the height will be accurate because the same table is used for the star and planets. So the height measured with sextant is this one here. Height measured with sextant is this one here. Sextant error was 2.3. That's the ship's device. And now I need to get these three errors. So for horizon dip, for 35 degrees, and maybe I'm going to need interpolate because it's not 35 exactly, it's 35 and a half. So this is 35 and 30 minutes, so 35 and a half. And the height of the eye is 21 meter. So let's go to the tables for height correction or altitude correction. And from the top I enter with 21, and from the left I enter with 35 and a half. So let's see what I have for 35. So the value I have for 35 is 9.5, and the value I have for 36 is also 9.5. So I do not have to interpolate anything. It is for sure negative 0 degrees 9.5 minutes. That's the dip correction. And temperature and pressure, let's see, it should be, both of them should be 0, but let's check them. So my height is 35, so that means I'm in the first column. My temperature was 10, so the correction for temperature is 0, and pressure was 1013, so that means both of these corrections are 0 and 0. So let's go back to the pattern of calculation. So we have height measured with sextant, we have sextant error, we have dip, we have temperature and pressure correction being 0, and after we do this, so this is 911.8 total. So that would mean the height is, what is that, 9, that's 35 degrees 13.1 minute. We can do that with calculator as well. And now we come to the difficult problem. Let's go back to the known star, step number 5. This is what I need. Step number 5, unknown. Let me just copy the formula here so I have them on one space. I need formula for this one and for this one. Okay, these two. Copy. So step 5 and 3.6. Now, we do not calculate height calculated because we do not know declination. So because we do not know declination, we are actually calculating declination of an unknown object. Now, declination calculated is how far the unknown object is from the equator, because declination is angle between an unknown object or celestial object and the equator. So in order to do this, what actually happens, because we have trigonometry rule, is this is side of the triangle, this is side of the triangle, and this is side of the triangle. So height is a side, latitude is a side, declination is a side. So if we do not know this side and we know this one, they just change places. So in our case, declination is the side that we are looking for. So that means it's sine of latitude times height, and we do not have calculated, we actually have height true. So those two just change places. And now the angle that is on the end of the formula is the angle that is opposite to declination, and the angle that is opposite to declination is actually our azimuth. So let me just take this mark here, compass reading. And that is how we got our formula for declination. So we have sine of declination equals sine of latitude times sine of height true plus cosine of latitude, cosine of height true, cosine of an angle that is opposite to declination side, and that is azimuth compass. And let's calculate this, because this is the first time using this formula. So we have latitude. Latitude is negative 36 degrees because it's south, and 26 minutes. So now I'm going to just copy this wherever I have latitude. Latitude is also here, so it's just repeating itself. And then I have height. Height is 35 degrees, 13.1 minute. So it's same here. So 35 degrees, 13.1 minute. And the azimuth was how much? How much was the azimuth? Azimuth was. Let's see how much was the azimuth. It was 334. 334 degrees. And that's it. So this is height, this is latitude. Is this correct latitude? Yes, 36.26 south, so negative. So let's put this in the calculator. So we start with sine. So sine of a negative value, 36 degree, 26 minutes, close the bracket, times sine of height, 35 degrees, 13.1 minute, close the bracket, minus cosine, or sorry, it's plus cosine of the same numbers, so negative 36 degrees 26 minutes, close the bracket, times cosine of 35 degrees 13.1 in time cosine of azimuth 334 degrees, close the bracket, press equal, and if everything is correct, shift sign to revert it, and we get, let's open it up, we get 14 degrees 22.5 minutes, and because we have positive result, that means it's north. So positive result means north. If we got this value negative, that would mean declination is south. Okay, and calculating local hour angle of unknown object. So we have now declination of an unknown object, but we cannot identify an object just by declination. We also need to know how far is an object from Aries So from spring point. In order to get that value, we need to calculate the local hour angle of the unknown object. So local hour angle here, we have azimuth calculated. So this needs to be replaced. We need to have local hour angle here. And it's going to be calculated. We're not going to get true automatically. It's going to be calculated. That's the rule, because the cosine function, I already explained that cosine function as a function cannot get value over 180, and local hour angle can be between 0 and 360. So that is why when we are calculating using the cosine function, we say that the value that we obtain is actually calculated, and then we're going to apply rules to get the actual value. So this is LHA calculated, and this is LHA calculated. So what's different in this formula here? So azimuth has declination opposite to it, so that means in this case height true is going to change the place, and this is where we're going to have declination and declination. So just three sides are changing their place, while latitude is always the same. Latitude we do not touch, so just height and declination, they change their spots. So we have height true here, that's 35 degrees, 13.1 minute. Latitude is, I'm going to copy it from here. When you are first doing the calculations, I always recommend to write down the numbers so you know what you are doing. And declination is last, so declination goes here, and declination goes also on the bottom. Okay, because this one is negative, this one should be in brackets. And then also here it should be in brackets because it's negative. I will later on do the aesthetics of this. And now let's calculate. Let's put all of this in the calculator. We're going to use this function here. So sine of 35 degrees, 13.1, close the bracket, minus sine of latitude, that is negative 36 degrees, 26 minutes, close the bracket, times sine of declination, 14 degrees, 22.5, close the bracket, go down and just repeat the last two numbers. So negative 36, 26, close the bracket, times cosine of 14 degrees, 22.5. Close the bracket, press equal, shift cosine, but let's just type the number here. So it's 0.9291432 and shift cosine equals 21.698, and I need to get that in degrees. So I press the DMS button, and DMS tells me it's 21 degrees, 41.9 minutes. So that is local hour angle calculated. I need to get local hour angle true. Local hour angle is directly connected with azimuth. So we have a rule here when we are calculating local hour angle and azimuth, that if local hour angle is greater than 180, then the true equals to calculated. If local hour angle is under 180, then true is 360 minus calculated. So always the connection between azimuth and local hour angle is that if one is over 180, the other one needs to be under 180. So in our case, our local hour angle is over 180, so it's 198, so 198, and our azimuth is 334. And now we are focusing on azimuth. The local hour angle of the unknown object needs to be under 180 because azimuth is over 180. So be careful. This number is not the reference point. This is local hour angle of Aries. Right now what we are calculating in step number 7 is local hour angle calculated of the unknown object. of the unknown object. And this value here, what we calculate, is actually referenced towards the azimuth. So we are comparing it with the azimuth. And if azimuth, and I'm going to copy this and make a note here, compass reading. So if compass reading is larger than 180 degrees, so that's the rule. If compass reading is larger than 180 degrees, that means local hour angle true is equal to local hour angle calculated. If compass reading, so azimuth, is under 180, then local hour angle true is actually 360 minus local hour angle calculated. So these two are the rules. So in our case, our compass reading is 334, so that means the true stays the same as calculated. That's 21 degree, 41.9 minutes. Okay, and now that we have this, we need to calculate sidereal hour angle. So what is sidereal hour angle? Sidereal hour angle is how far the object on the sky is from the spring point. So that means local hour angle true minus local hour angle of Aries. So we have 21 degree, 41.9 minus, and local hour angle of Aries is this value here. Copy. And once we subtract this 21 degree, 41.9 minutes minus 198 degree, 46.1 minute, we're going to get negative numbers. So minus 177 degree, 4.2. Now, sidereal hour angle cannot be negative. And because it cannot be negative, we need to add 360 to this one. So that is just the general rule for angles. They cannot be negative. So hour angle, bearing, course, bow angle, they cannot be negative. They need to be between 0 and 180 for bow angle, or 0, 360 for courses, azimuths, and hour angles. So let's see how much do we get. Plus 360, and we get 182 degrees, 55.8. So these two are actually coordinates. Let me copy them. Coordinates. Let's copy declination here. So these two are now our coordinates that we're going to use. So the blue values we use to enter almanac at correct date and look for star or planet that has matching or almost matching data. So now we need to go to almanac. And let's go to almanac, and here on the edge. So we look at declination, because declination can go from 0 to 90 degrees. So declination is going to give us less candidates. Once we find a star that has approximate declination, we check the sidereal hour angle. If sidereal hour angle is not matching, then we continue to look for another star or celestial object. So we start from the top of the list, and we are looking 40 degrees 22 minutes approximately north. So what has declination of 14 degrees? So first we have Aldebaran that has 16 degrees north. So that's 2 degrees off. That's too much, but let's say for the sake of the argument, if that is the candidate, let's check the sidereal hour angle. Sidereal hour angle is 290 and we need 182. So Aldebaran is not a candidate. So let's continue. We scroll down, 14, and we have the nebula star. The nebula has declination of 14 degrees north and sidereal hour angle is 1820, and that means our identified object is actually the nebula. So let me take a screenshot of this here and put it in my book. And let me turn back to book. And let me copy one of the shades. Do I have any of the shades here? Yes. Copy. And paste. Not you, not there. Come on, go here. Paste. Okay. And let me get the nebula. So here, let me zoom in. You see the nebula? Let me just take the opacity of this higher. Okay. So you see the nebula has declination of 14 degrees 31.5. So actual declination is 14 degrees 31.5 north, and actual sidereal hour angle is 182 degrees 37.5 minutes. So when we are looking for an object, we look at the declination column and then we see is the SHA matching. Now that we have matched, now that we have the identification, so identified body is star the nebula. And from the almanac, you take the actual values. So these two values that we obtained, they are just approximate values used for identification. So never again in procedure are you going to use these two numbers. They are over. We just calculated them to identify the body. And now that you know the body is actually star the nebula, you start over from the beginning by using this procedure here. Procedure for known star. So you start everything from the top knowing it's a star. So that's the problem with when you are observing an unknown object, that first you need to identify the object, and after the identification you have to do everything all over again with that information that you actually know what object it is. So either procedure for known star or known planet. Now, what if you looked all these lines here? Let me switch back to PDF. So you looked and you looked and you looked and none of the stars actually matches. If none of the stars actually matches, then here on the bottom in the right corner of the left page, you have sidereal hour angle values for planets. So one of these planets is going to match. If none of the stars match, then one of the planets is going to match. And once you find the planet that is approximately matching to sidereal hour angle calculated, you just also confirm that by looking at declination for that day. So if none of the stars is actually candidate, then it means it must be one of the planets. And this is how you read, is it a planet? So you have SHA of the planet here in the corner, and then you go here and you check the declination of that candidate. Is it matching to the one that you calculated? And if none of the planets and stars are matching, then you made a mistake in the calculation. Or you observed a plane. Or something like that. Okay. And that's it. That's it, I believe. Let me go back to the Word file. So we have known star procedure, where we find, let me just select all and remove this because it's bothering me. So this is Greenwich time, so this is universal time at Greenwich meridian. Yeah. Greenwich is capitalized, yes. And this is chronometer time of observation. And this is chronometer error. So once we have the correct time and date, you enter the almanac, and depending what you are observing, if you observed star, you start with spring point with Aries, and then you look at the star data. If you observed one of the planets, you look directly at the planet's data. And once you read that data, you put them in this pattern, fill them in. So let me see. So you have Greenwich hour angle with exact hour. Then you have correction for minutes and seconds. Then you put your DR longitude, sidereal hour angle of the star, if you know the star. And the end result is local hour angle. And once you have the local hour angle, you need to make sure that it's between 0 and 360. After you have that, the next step is correcting the height observed. Like I told you, all of these summarizations can be split individually, but we do not need the values of the summarization in between. We just need to get from height sextant to height true. And we use tables to get the corrections. And after we corrected the height, we have to calculate the height. And this value is actually where the object that we observed supposed to be if we are on our DR position. If we are not on the DR position, then we're going to get an error between the true, so measured height, and calculated height. And that error is in nautical miles. It can be negative or positive. And in order to get direction of the error, we need to find the bearing of the error, and the bearing of the error is calculated with this formula here. And then we have the rules. The rules between azimuth and local hour angle is that they cannot be both under 180. So if one is under 180, the other one needs to be larger than 180 because they are measured in opposite directions. And for planets, the procedure was identical. The only thing that was different is that planets have their own unique columns, and they also have their own unique corrections on the bottom of each page. So they have V and D value that you need to take in order to get the corrections. Also, for planets, you need to actually calculate the correct declination. For the stars, you don't have to, because declination of the star doesn't change by much during the year, not alone the month, during the year. Okay. And that was known planet. And then we had sun. Let's go to sun. Sun at any moment is calculated in the same way as star and planet. You need to get correct time, you need to get correct local hour angle, and you need to correct the height, and then you do the height calculated and azimuth calculated. So the procedure for sun in any position was the same. Why is the sun? Sun is capitalized. So, and there should be space here between this one. And then you get azimuth of the sun. And the next step would be plotting on the white chart. Okay. Sun at noon is a special procedure, so it's different from any other procedure. So it has its own unique pattern of calculation, and it starts with you reading the value of meridian passage in the lower right corner of the almanac. And once you do that, so what was the date here? Date was 23 of July. So 23 of July, meridian passage is on 11:58. And once you have that time of meridian passage, you read the declination. And now to get latitude of meridian passage, you have 19 minus height true plus minus declination, and you get directly latitude of meridian passage. So that's the advantage of Polaris star and observing the sun at noon, is that you directly get your latitude of position. You don't have to calculate the additional line for latitude. You only get you get latitude directly, and you only need to have one more observation to get longitude, but latitude is already calculated. Sunrise and sunset procedure was to calculate deviation of magnetic compass. You can calculate deviation of magnetic compass in celestial navigation by observing the sun, any of the stars or planets, and Polaris. But the most two common procedures are sun and sunset or sunrise moment, or Polaris star, because they give value of azimuth true very easily. Sunrise and sunset is a small formula, this one here, so much smaller than the other formulas. And for Polaris, there's no formula, you just enter the table and read out the value of azimuth. So that's the advantage of sun when you are observing it in the moment of sunrise and sunset, and Polaris star. And then this is what we did today. And now I have to do the decoration of all of this. I need to make spacing correct. I need to put brackets where they're supposed to be for negative signs and all of that. I will do that offline. If you have any questions about this, you can ask me, as you already know, in the comments below. If you want to have additional videos recorded or tutorials for something, let me know, send me a message or an email. If you want to know how to support this channel, you have all the links in the description down below. And I will end this for today. We are finished. The next step would be plotting on the Y chart, and that will be during the next week. I will record that during the next week because I want to finish this document. I want to make all the decorations so it's ready for students. So I'm going to decorate all of this. I'm going to make numbers larger, smaller, create space, and all of that. Okay, talk to you next week. Have a nice weekend, what's left of it, and goodbye.